See, I can record these and put them up for you because you'll come to class. I have to worry about others.
Yeah.
You're like, oh, I'll just go to the recording and not come to class. I did look, it's your Balmer series. It's going to be your visible light.
I see. So the rest are like ultraviolet or like.
Some would be X-rays, ultraviolet, infrared, stuff like that.
Okay, I see.
Okay, so we were talking about the wave function. We found out that your wave function can take a form of e to the ikx. So what we didn't get to last time is we're going to say, well, let's test that. Okay, so let's do our second. Let's work through our second derivative. I want to give you another definition of second derivative so that you can think about it.
Okay.
Can you see how we take take one derivative, then take the other, and that equals the second derivative? That's because you can break them apart like that. So you see how we can take the first one and then take the second one, and that equals the second derivative.
Yeah, for sure.
Because we're going to get to a point where you're doing multiple integrals and you're just working from the inside out. So you can see like, oh goodness, a triple integral. How do you do that? Well,
integrate the double integral.
You start with, you'll see the multiple integral signs.
Yeah.
But then you look at the order, then you'll have like dx, dy, dz at the end. And you look at the order of those. So from the inside out, your first integral sign is the integral over dx. You solve that. Then you put that solution into the next one. Your next integral sign solves for dy. Then you put that solution in. You just work them inside out. You don't do them all simultaneously.
Do you have to like move the boundaries of your integral, or are they?
No, your boundaries can stay the same.
Oh, okay.
Because the boundaries on like y and z don't affect x.
Right.
So you just solve for x, and you have that solution. Then you solve for y, and then you have that solution. So yeah, you just look at them and go, oh, I'm inside the nut, and I'm going to work my way out.
Yeah, for sure. It's like an onion.
Mm-hmm. Yeah, multiple integrals are like onions.
Okay, perfect.
You work your way out from the inside through the various layers. Okay, so let's look at this ikx. All right, so what happens when we take? Let me get the. Okay, so the first thing we're going to do, e to the ikx, we're going to do u substitution. Oops, not du, dx. So we have that. So you see that as we're going through, the calculus itself is not super hard. Because I mean, we could do that first derivative all day long. Now, we're going to do the chain rule again, where we're going to, and so this up here was du dx. So remember, our chain rule is now going to be du dx du over e to the u. And so we know that d du e to the u, that's going to give us du dx e to the u, because that the derivative of that exponential function just kicks it back at us.
Right.
It's one of the nicer ones. When you see it, you're like, oh, good. Yeah. You start also to get to the point where you see natural log. You're like, oh, that one's an easy one.
Okay. What is it for natural log?
So if you did natural log, it's always that.
Yeah.
So you start seeing those, you're like, I can do it. Or if you see an integral where you have like 1 over your variable, a lot of people freak out and go, oh, what do I do? You're like, as you get better at physics, you start to go, oh, this is going to be a natural log.
Sure.
Okay. And this is one of the way. And sometimes math does work like biology. Some of these you start to recognize because you use them so much.
Yeah, you just memorize them.
When you take PChem with me, I'm also going to have you get a book called Shalm's Mathematical Outlines.
Mm-hmm.
If you want it early, I'll show you what it is. But it's a book filled with tables of integrals and derivatives that mathematicians have already solved. So you're like, all I got to do is some algebra, make my integral look like this, and now I have the solution. Mm. So it's kind of helpful. Drives math professors nuts because they say we're cheating. I'm like, dude, my job is not to solve the integral. That's your job. I'm
Sure.
trying to model a physical system. Okay, so now we know our du dx is this, and our e to the u. So our du dx is going to be ik, and e ikx. Okay. Now we could go through this process again, but I think you're kind of getting used to how this works. We would take now we would take another derivative with respect to x of ik e to the ikx. The initial ik being a constant, it's going to pull out front. And we would just do the derivative of e to the ikx again, which we've already solved. So that tells us that if we did we know that every time we solve this, we're going to get a factor of ik, right?
Right.
So now we're going to have ik times ike ikx. And then we're going to, so when we multiply that in, we're going to get I squared, k squared, e ikx. So now what do we have here?
The imaginary number.
Yeah. And so what does I equal?
It's square root of -1.
-1. So what is I squared?
It'll just be -1.
-1 equals negative k squared e ikx. Well, I'll be darned, that's exactly what we're looking for.
Great.
So now we have our negative k squared times psi. All right. So now what we know is this is a solution. Now, you can work through this. You'll find it ends up being the exact same thing. We also know that another solution is e to the minus ikx. Those are both solutions. Now, one thing you're going to find out about differential equations, every time you find groups of solutions, a linear combination of those solutions is also a solution. Okay. And so you could just over time, you could just play with that. You could find like multiple solutions, add them together in a linear combination, and try all your derivatives again to see if they still produce the same answer. They will. Okay. So what do we mean by a linear combination? Well, that means, how far am I in my notes? I tested the negative ikx, trust me, it works. So the linear combination, and this is where you'll see this in a lot of books, and they skip telling you this part, but this is what they're saying. They found these solutions. Well, the linear combination is itself a solution. So that means we're going to do C1 and you don't always know what these coefficients are. You have to have them in a linear combination. Okay. So this is what we mean by a linear combination. So this here is itself a solution. But we are looking for a wave function. Okay. Now exponentials, I mean, they'll produce kind of a wave. They produce more growths or decays. But we know that sine and cosine produce nice waves. So we can start to evaluate waves in terms of sine and cosine, but we don't have this in sine and cosine. That's where our old boy Euler comes in. So we go back up. Now we're going to be using Euler's formula to replace the e to the ix or the ikx with sine cosine combination. And so you just follow the plus or the minus. So if you have e to the positive ikx, it'll be cosine kx plus I sine kx. And if it's minus ikx, then use the minus sign.
Perfect. Makes sense.
And so what we're going to do is now our psi. So you see all this space. It's not that the math itself is super difficult.
Yeah.
It just takes a while to write it all down.
Yeah. And you need explanations for it.
And so I'm going to take that first ikx. And with Euler, I'm going to get cosine kx. Go home and tell your dad about Euler. He'll be so happy.
Great. If I pronounce it right, he'll be happy. I should be like, I learned about this guy named Euler today.
Poor dad. So you see, we use the plus sign there because that was our positive ikx. Now we'll do C2. Okay, so now we've translated in our Euler for our exponentials. Okay, now let's start combining terms. Okay, so C1 cosine kx plus C1I sine kx, C2 cosine minus, minus C2I sine kx. Now we're just going to combine. This will combine into C1 plus C2. That's a bad C. C2 cosine kx plus. Now watch this. Here's what we're going to do here. We're going to do I C1 minus I C2 sine of kx. And then what these are going to become is these are our new coefficients. And this is then a lot of textbooks skip this whole central step and they just say, well, the solution to the wave equation, we get the more classical version where we're going to get A cosine of kx plus B sine of kx, where our i's are absorbed into the new coefficient. And this is the solution a lot of textbooks give you. They just skip straight to here. Now, granted, as I told you, start playing with derivatives of sine and cosine. You'll find that you could actually just start there, but it's not as intuitive as starting with the exponential, because one of the first things you learn in calculus is that the derivative of that e gives you the same function back. And we knew that we were looking for a function that would give us, after two derivatives, would give us itself back plus some a square of a constant. It's like, and the more used to it you get, you'd be like, oh, that's going to be the exponential. But if you start playing around with the derivatives of cosine and sine, and again, you did u equals kx, you'd still pretty much end up there.
Sure.
Okay, so here's our general solution to the wave equation. Now, we want to take this a little bit further. Now, this is where some of the physics comes in. Do you see remember the well we made? We're now going to apply what's called boundary conditions. Looking at that, what do you think the boundary conditions are? We know V is 0 inside the well.
Boundary conditions?
Mm-hmm.
Like, I don't know what that means.
Well, what do you think the boundaries of that well are?
Just the values of x on the
Yeah, x equals 0, x equals a. Those are our boundaries.
Okay.
So now, let's walk through boundary conditions so we can see what it looks like to apply those. So we know at the boundary conditions, if I say, well, originally I have a function psi of x. Then I'm going to put those boundary conditions in. So psi at x equals 0 is going to equal psi at x equals a. And since those walls are infinite, what do you think psi becomes at those boundaries? You're in a bound state. Those are infinite walls. What do you think happens to the wave function once it reaches those boundaries?
When it reaches the boundaries?
Mm-hmm. At 0 and a. You saw the wave exists in the well.
I mean,
once it reaches the infinite wall of that well, does it escape the well, or does it cease to exist?
Would it escape? No.
Nope.
Okay.
So at the walls, it's going to disappear.
Okay.
So this is some of the stuff that you get used to as you study this more. This is a new idea you've never heard of or seen boundary conditions. You have to start thinking about the physical reality, like, well, it's an infinite wall. There is not going to be a wave function outside of it. So once I hit either one of those walls, the wave function disappears. Okay, so let's look. So what do we say? Psi of 0. Okay, well, that's going to be A cosine of 0 plus B. So really, we're just putting the x value in here. And we know that this equals 0. Okay, so what is sine of 0?
0.
So that's going to disappear entirely. What is cosine of 0?
1.
1. So what we end up with is A equals 0. So what does that do to our wave function?
I don't know.
If A equals 0, what does sine equal now?
Is it just 0?
Mm-hmm. A equals 0, we'll get rid of what term?
A equals 0, we'll get rid of the cosine?
Right, so what we're left with okay, so now we're here. Okay, now we want to apply, we want to look at our boundary condition at A. So we know this. This leaves us with a couple of options. Okay, could be that B equals 0. If B equals 0, then we have no wave function. We have a trivial solution, which can't represent a physical situation.
Sure.
We know there still has to be a wave function there. So a trivial solution, and that's automatically got to be thrown out. But if I want sine to continually yield zeros, where does that happen?
If
Where does sine equal 0?
at 0 or
At 0, at
isn't it pi?
pi, then
2
again
pi,
2 pi.
3 pi.
Yeah.
Yeah.
So sine of some value equals 0. Pi. Oh wait, hang on. Got to always remember to put in at the origin. Pi, 2 pi, 3 pi, so on and so forth. Okay. And technically, this would be like plus or minus pi, plus or minus 2 pi. It doesn't matter which way you're going. But yeah, so we know that this sine function will continually yield 0 at these values. Okay. So what that tells us is that Ka is going to be some value of n times pi.
Yeah.
Okay. And when I solve for my K, I get n pi over A, which will then give you the, we're not going to go through normalization. We don't need to do that in this class, but this will give us the non-normalized general solution for the wave function of our electron in the infinite square well, or in a bound orbital. Sine. And so we know K is n pi. So that's going to be n pi x over A. And you'll see this general solution all over the place, but this is how you get to it. Now, the question is, what kind of energies are we looking at for those electrons? Okay, well, we remember where we started with K, 2me or h bar. But now we also know that K equals n pi over A. Okay, so then let's just start multiplying through. Let's square both sides. 2me, and we could probably change that to m sub e mass of the electron, or h bar squared, and give us n squared pi squared over a squared. And when we solve this, So these are going to be our energy levels for that electron. And so you're going to start learning terms like hydrogen and hydrogen-like. We can solve the wave function exactly for hydrogen and hydrogen-like. And we can use these solutions as approximations for other atoms. Like for example, when we get to helium, do you know a famous problem in physics why we can't analytically solve helium?
Is it like, I've heard this before, like the two body versus three body?
Yes. Mhm.
Okay, because there's two protons and now you can't
Well,
calculate.
no, hydrogen-like is proton, or not just proton, but positive core
Positive four
electron,
electron.
two body.
Right.
And so you're not looking at the number of protons. It's just a matter, here's a force producer, two body.
Sure, okay.
Once you get to helium and beyond, you have the three body and plus.
Because you have more electrons.
So like helium, you'd have to start dealing with electron repulsion, electron attraction.
Mm.
You start have to dealing with angular momentum. Like it becomes a mess. So we feed stuff like this into computers, and then they start doing things numerically, and they come up with solutions for the beyond the two body problem. But we can't do it analytically. Anyone who ever figured out how to do the three body problem analytically will win a Nobel Prize.
Great.
Okay, so now here's a question. Why did I write this as E sub n? What are we looking at specifically here? This is equivalent to the Bohr model.
So this is energy at different levels?
Yes.
Yeah.
N is your principal quantum number. So these, and with this one, if you want to compare it to the energy they come up with in the book, you can play with, for example, your H bar is H over 2 pi, stuff like that. Your M is going to be the mass of your electron. So, so on and so forth. Okay.
So, okay, in that case, yeah, N is like first.
Yeah.
Number.
Well, so yeah, your principal quantum number. So like your 1s, 2s, 2p. Those numbers are your values of n.
Okay.
Those are your energy levels.
Perfect.
And so see, I gave myself more room than I needed.
Okay.
So now we're not gonna go. So you've seen the basic way that we end up getting wave functions. Now, as we start dealing with electrons and orbitals, the actual wave functions that are solved for in chemistry are going to be combinations of radial and angular components. Those angular components, the A there, those are called, so if you were reading and someone says spherical harmonics, that's the A part of the wave function. Okay, those are your spherical harmonics. And so, of course, all of our wave functions are so your radial part is going to be from the center of the atom out. So like your rho value, and your spherical harmonics are part of theta and phi. And you remember in general chemistry, when we're learning about all the quantum numbers, N, L, M sub L.
Yeah.
This is where they're used. They're going to parameterize your wave functions. Let's take a look here. Look how these change. So what you're going to see is you're going to start seeing wave functions. Which one up there do you think is the 1s wave function?
Probably just the most simple one.
Yeah, it's the very first one. Look at the quantum numbers in the far left column. So your 1s, so your values for your wave function are always going to be psi of n, l, m. Those are your principal angular momentum and magnetic quantum numbers. Okay. So psi of 1, 0, 0, that is your 1s shell or subshell. And you'd multiply all these together to end up getting the total wave function. Okay. Mm-hmm. So look at these numbers down at the lower right. That tells you the shell you're in. So you see your 2, 0, 0, that's 2s. Because remember when we went through that, and we'll talk about it like quickly. Like your L equals 0, that's your S subshell. Right. M sub L has to be 0 if L equals 0. Yeah. Now look at your 2, 1, 0. What is L equals 1? Do you remember what subshell?
Is that for P?
P. So that one right there, that's your 2p0 subshell. Then you have your 2p plus 1 and minus 1 wave function. Do you see it? And Do you see how the quantum numbers now parameterize the wave function?
Yeah, that looks good.
So when I was saying in general chemistry that these mean quite a bit more, we just can't go into it. This is where they start coming into play.
Right, okay. That makes sense.
The quantum numbers are going to define the space your electrons live in. And so as kind of a visual, all those wave functions you see up on the table above for the hydrogen and hydrogen-like compounds or atoms, here is your solid wave functions. These are your highest probability areas for your electrons. This is how the electrons themselves will space out into waves. This is what the waves look like.
So when it says plus and minus, it's not talking about charge, it's talking about like
Phase.
phase.
Yep.
Phase?
Yep. You remember, and we'll talk about that in a
You
minute.
did phase diagrams.
Not so much. This is more of like a shifting of the wave to a completely new phase. And do you remember your diagrams where you'd have like your p orbitals and they'd have one color and another color?
Yeah,
That's your plus and minus.
right.
Those are your two phases.
Oh, okay.
So that's what it's looking at, plus to minus, phase to phase. But this is what your orbitals are actually going to look like, and then you get a combination of them within every atom. Okay, so something that should be quite a bit easier though. Oh, and I wanted to add one thing up here. So I talked about multiplying these together. If you stretch this out more, so your psi, let's see, and Ln. So your radial part brings in N and your angular momentum. Your A brings in angular momentum and magnetic. Just don't have quite enough room here. Your A can then also be separated into, let's try and do capital, a theta portion and a phi portion. So that lets you know that your psi is going to be R times theta times phi. So you can actually break it apart even further. And that's how you know how to take these individual pieces and put them together into an actual wave function. Now, and again, what you see here, this is the wave function unparameterized, just change y with a. But you see how you see your N in the radial part. If you broke that y apart, you'd start seeing thetas and phi's where you plug them in. You start to see how you would actually start to plug things in here.
Yeah.
Yeah.
Yeah. 1, 2, 3.
Mm-hmm.
I see.
So the one they actually have written out there, that's your radial portion.
Mm.
And that L that you see there, we're not going to go through those because you don't really need them for your career, but those are called Laguerre polynomials. In quantum mechanics, you end up having a whole chapter in your textbook on Laguerre. Laguerre. I never know how to pronounce the name. It's Laguerre. UERE, something like that. It was another European name. Okay. Now, let's see, calculate the energy in kilojoules per mole of photons of a spectroscopic transition, the corresponding wavelength, which is 450 nanometers. Can you do that?
Okay, so it's saying the wavelength that's emitted is 450 nanometers?
Yep.
Okay.
In the same jump, it either absorbs the 450 and jumps up or falls down and it re-emits the 450.
I see. Okay. I don't know. I don't know where to start.
Let's keep this one super duper simple.
Okay, super simple.
When we're doing energy transitions from one level to another, what equation do we use to figure out the energy of the photon that's released or that's absorbed?
Is that there's so many slides. The EN one?
Nope. Keep going back.
Going back.
This, because we don't have a value of n here. We don't.
Oh, right. Okay, no value of n.
You could use that if you did, like, let's say it jumped from n equals 2 to n equals 4. You could calculate that twice and then do delta E between those two. We have a much simpler equation that gives us a delta E. Mhm.
Here's Is it? This one has an H bar. No,
Keep going back.
keep going back.
Yep. Oh, you're almost
Oh,
there.
this one.
There you
Oh,
go.
the Planck.
Yep, the Planck equation.
Okay, delta equals HV.
Mhm.
Or sorry, no,
Well,
it's a new.
new, but then we have a wavelength of 450 nanometers. So let's use E equals HC over lambda.
I really did want to make that harder.
Yeah, and that's the thing. We go through the hard part, so you know how things are modeled, where they come from.
Sure.
But then a lot of the times solving things, you go back to the easy portion. Now, keep in mind in a spectroscopic lab, you would need to know the harder part because the Planck and the Bohr model can only get you so far. Because, for example, in the Planck and the Bohr model, every value of n, all of the orbitals are degenerate. What does that mean?
Degenerate?
Mm-hmm.
Oh my gosh, I really should know that word.
Not degenerate like your little sister or something like that.
Okay. Oh my gosh, I don't remember.
It means everything is the same energy.
Same energy.
But we know, for example, like inside of the n equals 3 shell, we have subshells of S, P, and D. According to Bohr, those are all the same energy, but are they actually?
I guess maybe not. I don't
No,
know.
they're not. Your S, P, and D subshells are going to be different energies, and we're not actually going to solve for that. That is a huge thing to solve for, but you'd have to start taking all that into account in a spectroscopic lab, where you're also taking into account electron penetration, electron shielding. You're going to be calculating in energy for repulsion, we're going to, you have things called exchange energy. So a lot of this stuff you would learn throughout, say, the course of a doctorate, where it would all be towards analyzing spectroscopic data. So like you'll see in a little bit, those electron configurations that we have?
Yeah.
Those ground state electron configurations were all figured out by spectroscopy.
Cool.
So it's a major field if you can get good at it.
Yeah.
Just very few people can get good at it. So what do we have here? Well, H 6.626 10 to the negative 34th joules times seconds. Speed of light, we're just going to use 3.00 times 10 to the 8th meters per second. Over. Now, what's the quick way of turning 450 nanometers into meters?
It just moving decimal or 10 to the negative 9th.
There you go. So yeah, anytime you want to take a nanometer to a meter, just slap onto the negative 9th. When you multiply this, now here's a question. It's asking for, now if we get it in joules, we can translate that, that's fine. But this is in joules. We want this in joules per mole of photons.
So do you need Avogadro's on it?
You do, because remember, Planck's equation gives you the energy for one photon. Okay? So that's one of the little tricks. This is energy per photon. So what we do then is we say, well, I'm just going to do this the old-fashioned way. I say, well, per photon. Okay, well, I'm just going to say 1 kilojoule. 1,000 joules. Instead of playing with moving decimal places, I just let's just put everything in the calculation and use our calculator once. Now, do you remember how we would put Avogadro's number in here?
You want the Avogadro's number on top?
Yes.
It's on the photon?
Yeah. So yeah, it's going to be, because remember, Avogadro's number is a mole of anything.
Yeah.
6.022 times 10 to the 23rd photons per mole. When you calculate this, you get about 266 kilojoules per mole. So not the hardest thing to solve, but you do have to take some things into account.
Yeah.
Remember some things, a few little tricks, like Planck's equation always gives you the energy of one photon.
Yeah.
In general chem, for some reason, I could not get that through to some people. I'm like, it is one photon, one.
That's funny. This does feel like just like Gen Chem. This equation
Yeah.
brings me back.
Well, and that's the part of these first two chapters. We're combining things you learned in Gen Chem with deeper meaning.
Yeah, for sure.
So it's like sometimes when kids, I'm in my 40s, but when people who are freshmen and they get mad, like, well, why don't you just teach us the way it really is? You're not ready.
Yeah.
You're not ready. You need some years of, you need math classes.
Yeah, I would have been scared if I saw that.
You need some years of shoving stuff into your brain and creating some new folds before we go too much deeper.
Yeah, that's true.
Because again, yeah, even the best students in class will go, whoa, whoa.
Yeah, you need to do this like junior year when they're already locked in enough, like they can't drop out.
I mean, think of some of the stuff you learned in microbiology in year 2. If they had done that to you in year 1.
I did it in year 1, but it was like, it was shocking. I don't know.
I always did think you were a psychopath, but that's okay.
That's okay. That's okay.
Okay, so now atomic orbitals. So we remember we have our basic quantum numbers in L, M sub L. Again, principal quantum number, angular momentum, and magnetic quantum number. And here's the values that they can take. We know that our orbitals, every orbital is defined by 3 quantum numbers, N, L, and M sub L. So just as an example, we have the xenon ground state configuration, okay? And we know that each one of these 1s, that's going to be N and L, 2s, N and L, 2p, N and L, so on and so forth, okay? So let's talk about our values for L. I mean, we see up here that our values can go from 0 to N minus 1. So for n equals 2, that's going to go 0 to 1. So in n equals 2, that's why we only have the p subshell. We have s and p subshell because L equals 0. So you see they line up here. L equals 0 is your s. L equals 1 is your p. 2 is d. 3 is f. So, and these are fun. I actually made these with a computational chemistry program, because if you tell it how to calculate a proper way, I told it to use the Hartree-Fock method, which is more generally called the wavefunction method, and told it to use a nice high basis function, so these would be accurate. Here, these are, for example, your p. This is the example of a p orbital, and then you have an L equals 2, which is a d orbital. So again, here you can see the phase change.
Yeah.
And then right there in those middles. So how many, start and think about this. How many nodes do you see on the p orbital?
Just the 2. All right, so is the center a node?
The center, yes.
Yeah.
So we're not looking outside the orbitals. You have that node right in the center. How many nodes then does the d orbital have?
I guess, isn't it 2 because there's 1 for each of them?
It's 2.
Yeah.
So think of them as planes, nodal planes.
I see. Yeah, because you could draw like a.
Yeah, and I want you to start to get used to that too. So if you think about, let's just say we drew like a little. We just drew a little plane there, okay? That's our nodal plane. No electron density can exist there. I want you to start to get used to visualizing these structures that aren't actually there, because you're going to need to, you'll need it for molecular symmetry. So keep in mind, L is the one that tells you the shape of the orbital you're looking at. Now, your quantum number M sub L tells you spatial orientation. Now, a little deeper than we got in general chemistry, because we talked about the fact that each one of these is going to represent one of your magnetic quantum numbers. So like, I can't really do this because this is X, Y, and Z. But we know, for example, that PZ does line up with M sub L equals 0. Okay, we know that. And do you see why they're called PX, PY, PZ?
Yeah.
Because they lie on those axes.
Right.
Okay, so now the thing we couldn't cover, and I still had people try to do this. They would say, oh, well, one of those is +1, one of those is -1. No. Remember how we said that any solution, you can form a new solution to a wave function by doing a linear combination of other solutions?
Sure. Yeah.
So in reality, your PX and PY oops, we need another coefficient. And then your PY is a linear combination of your +1 or they're linear combinations of your +1 and -1 wave functions. So that's how PX and PY actually line up. Your PZ lines up with the magnetic quantum number of 0. So just a little bit deeper in there, knowing that a lot of this, and it really starts to get across the idea of the mixing of energies to form different realities inside of these atoms and inside of molecules. Because these wave functions are now going to have to either mix additively or subtractively to form these actual orbitals.
Right.
And of course, and now this one I wanted to put on here because I really want you to I want you to get used to the shapes of these d orbitals, because this is going to become super important when we talk about crystal field theory and d orbital splitting in metals. Okay, so I want you to understand these 5 d orbitals.
The funnel one's funny looking.
Well, yeah, I always call that the donut one.
The donut.
So if you take the funnel away, that green in the middle looks like a donut. But that's your dz squared. But let's look at some of the others. Your dxy, dxz, dyz. How can you see how those are different from the dx squared minus y squared?
Yeah. Yeah.
How are they different?
It's like on the axis versus in between it.
Right. Your dx squared minus y squared, they lie on the xy axis. All of your others, they lie in between the axes that are represented in these subscripts. So you notice how the dxy, the lobes, lie between the x and y axes.
Yeah, I see that.
So again, this is going to become important when we start talking about crystal field theory, d orbital splitting. So this would be a good slide to review from time to time to make sure you got those shapes in your head.
Page to outline.
Yes. Okay. So we're going to start talking about specifically the radial part of the wave function. Now we're going to go beyond orbitals beyond what you've studied before.
Sure.
So first off here, like just look at the bottom. You see those multiple S's?
Yes.
And you see how you get node, node, node every time you get a new S shell. Now, that's the first thing we want to learn. We want to make sure we know that we have these areas of 0 electron probability. Those are quantumly disallowed regions. Okay? That will seem to be counterintuitive when we talk about electron penetration. But just because your 2s penetrates into your 1s level does not mean that that node disappears or that your energy becomes a spectrum. Welcome to quantum mechanics.
Okay, cool. Whatever.
Particles are assholes.
Yeah. I guess they can do that.
But we want to start learning how to read these graphs. So if we look at our wave function versus our radial distance out from the nucleus, and again here, if you go back up to the table, I've put together your 2s radial part, your 2s radial wave function. See how it's the 2, 0, 0?
Yeah.
That is your 2s. N equals 2, L equals 0. That's 2s. And again, I keep going over this because this wave function right here, the way that's represented, you won't see the whole thing written out, but if you pick up an article, you will see orbital or wave function 321, like 321, 320.
Right, and it's just telling you
yeah.
what it looks like.
So, and you need to know how to read that so you know what orbital they're talking about. Now, this graph suggests you want to make sure you're not taking things out of figures that aren't there. This graph does suggest that electrons you might think they go all the way into the nucleus, that they fall into the nucleus. But what did we say about that?
It just won't happen.
It's not possible because that's not a quantumly allowed state. So unlike how a planet could spiral into the sun, because gravity does actually have a spectrum, which is weird that it has a spectrum, but it's also quantum. We're still working on that one. But so that's not what this is saying. What this is telling you is that as you get closer and closer and closer to the nucleus, for these individual wave functions, you notice how the 1s has most of its representation very close to the nucleus?
Right.
So that matches up with that 1s that 1s shell. So that 1s subshell, most of your electrons are going to be as close to the nucleus as they can get. That's what this graph is saying. Your 2s subshell, do you see how you get more representation further out?
Yeah.
And then you see how it crosses the 0 line?
Yeah.
That 0 line, every time it crosses 0, you're going to get a node. So if you did a 3s, then you see how the 2s crosses the line, then comes back up to 0. And what that's saying is you get a certain distance out from the nucleus, you have no electron density. Okay. That's when the line hits 0 on the x-axis. But that 2s crosses the 0 line, so that's your node between 1s and 2s, and then goes to 0 as you go further out. Now, if you look at the 3s, what you would see is a line come down. It would cross. So it'd be kind of like. Let's see if I can do this neatly. It'd be kind of like this, where it would cross, okay, and then it would cross again. Well, I need to. And then go to 0. Your 3s would look something like that. So you see now you have the 2 nodes.
Right.
Every time a graph like this crosses the 0 line, that is a node between one shell and the other shell. And we'll look at this slide and then call it a day. So again, you see your radial wave function versus R for several different representations here. Now, why, for example, okay, look at your 2p. Why does your 2p not cross? Because we said that the p orbital has the nodal plane right in the center, but why doesn't the 2p cross the 0 line? Why do we not see a node there?
Because I mean, that's the start. The start is at the 0.
Because in this case, we're only looking at radial nodes.
Only looking at radial nodes.
So you see how your 3p crosses once? And so what you're looking at then is your radial node. If you look here, your 2p has nothing beyond itself. There's not a radial node to represent. Your 3p, see these outer lobes here?
Yeah.
And you see how when you actually calculate these quantum mechanically, you see how the 2p doesn't touch the 3p?
Yeah. That's
your radial node. So you're going to get this disallowed electronic region as you cross from one value of np to the other value of np. You're going to get that radial node going out that way, and that crossing the 0 line right there on the 3p is this radial node right here.
Sure. So are we just like with any orbital, we're just going to assume that there's no electron density at the nucleus, or are we?
Yeah, well, yeah, and because it's disallowed.
Yeah.
It can't happen. And so that brings back in our idea of quantized energies. So yeah, even if they wanted to, electrons couldn't simply spiral into the nucleus.
Sure.
So that's what we have to kind of think about that when we're looking at these graphs, and we're taking that into account. Well, they can't actually reach the nucleus. So what is this telling me?
Right. Okay.
So we're trying to learn to read figures based off physical realities.
Sure. We don't need to consider that when we're doing a graph like this.
But yeah, you'd have to imagine in general chemistry, this one here would have driven people nuts.
Yeah,
Well, 2p, 3p.
2P, 3P.
And they would just keep going on and on and on as you got out higher and higher energy. You can get some that just look like a giant butterfly as you go on and on and on. And then, of course, you want to make sure you get that you have minus, plus, plus, minus. So you see your phase shift.
Right.
Okay. So sadly, we won't meet again until next Wednesday, but
True.
if we keep up this pace, we're going to do pretty good.
Yeah, that's okay. I'll definitely read what the book has to say about this part, because I remember reading it and I think it made quite a bit of sense, but I'd like to look at it.
Yeah. And I do. I like her writing. I think her sections are concise and they're nice to read. So
She explains big words when she uses them. I like
oh
it.
yeah.